So, welcome to this class on hardware security. So, we shall be continuing our discussions on power attacks. In particularly, we shall be talking about how to to understand on CPA or correlation power attacks, and we will be trying to see how we can implement CPA on simulated traces. So, as we were discussing in the last class, in correlation power attacks, like the DOM, right, you basically develop, you go to your target byte location. But after that, right, there is a slight subtle change, like in the difference of mean, right, you are basically trying to calculate one of the bits, for example, but in a difference of the difference that is, or the subtle change that is over here is that you are trying to apply a powered model, and rather than predicting or getting one of the key bits to kind of split the power traces as we were doing in DOM, what we try is we try to develop a hypothetical power trace of the device for a given input to the cipher. So, these hypothetical power values are then stored in a matrix for several plain texts and can be indexed by the known value of the cipher text and the guessed key byte. That means, you can kind of index the hypothetical power traces based upon your cipher text portion and also the portion of the guessed key byte, and this matrix is formally defined as H, or the hypothetical power matrix. Okay. And you also have another similar matrix which is called as the real power matrix, which is denoted as T. Here the attacker also observes the actual power traces and stores them in a matrix for several inputs, and the actual power values can now be indexed in this case by the known value of the cipher text and the time instanced when the power value was observed. Okay. And this matrix is denoted by capital T, which is the real power matrix. So, it may be observed that one of the columns of the matrix H corresponds to the correct key, which is K star. Okay, that is one of the columns of your matrix H. That means, your hypothetical power matrix is where your correct key is essentially coming into play, and that is essentially denoted as K star. So, what you try to do is you try to, in CPA, you try to compute the similarity between the columns of the matrix H and the columns of the matrix T to distinguish K star from the rest. Similarly computed, in this case the similarity is computed by using Pearson's correlation usually. Okay. So, what I mean to say, let me elaborate here. So, basically what I am trying to say that is you have like the last round of AES. So, consider that this is your 10th round of AES, okay, where you are essentially calculating the cipher. So, this is your corresponding cipher text, and you are targeting, say, one specific byte of the cipher. Okay. So, what you are doing here is that you are basically trying to get back, but if you want to get back, then you have to guess this key, right, because there is this 10th round key which comes in between. Again, right, what we have seen in DOM, right, you do not guess the entire key, but you guess only a portion of the key. Say I guess this portion of the key, and then you apply, if you want. So, there are this bundle of S boxes. So, there are 15 S boxes over here, but if you want to go to the input, then you basically need to invert, say, one of these S boxes. So, this is your, say, S inverse, which means the inverse S box. Okay. So, the idea is that when you are doing when the AES hardware is like working, at that point of time you try to you basically kind of take the power traces and you store the power traces in the form of a matrix. Okay. So, this matrix is what is called as the real power matrix, or T. Okay. So, in T you are basically kind of indexing T by the number of samples, like suppose you are encrypting, say, 1, 2, so on, maybe 10,000 plain text, for example. So, this is essentially like, say, 0 to or whatever 1 to 10,000. So, these are all the number of encryptions which you are doing, and the row essentially is the time instance. So, this is that like your T, for example. So, therefore, right, any row that you basically have here, you basically are some way like having your AES power trace, and you are sampling that at different time instances. Okay. So, this is your T and this is your power consumption, and all these real values are being stored in this table. Okay. So, therefore, this table is basically a like a representation of your actual power consumption. Okay. So, now you are trying to develop the hypothetical power model. Now, for the hypothetical matrix, which is essentially denoted as the matrix H. So, what again like you have got this 10,000 encryptions, Okay. But for all of them you are basically making a guess. Okay. So, you know that there are, when you are guessing this key byte, you do not know what is this key byte. There are 256 possible values of this key, right. There are 256 possible guesses which are possible of this key. For every guess, suppose, you know, like let me write this guess as k0. Okay. Say I guess this k as say 0 as one of the key. So then I like I take each of these cipher text. Suppose I take the first cipher text. Okay. Say let me call it as, you know, like C. I XOR it with k0 and I calculate the inverse of it. Okay. I calculate say S inverse. Okay. And then I basically find out the Hamming weight say of this value. Okay. And that, so I basically I can apply any power model for that matter, and whatever is my favorite power model, based upon that I get an integer value here and I store that value over here. Okay. So like this, right, I basically do it for all the possible ciphers. Okay. So therefore, right here this is indexed by say 256 because there are 256 possible values of the key. Okay. So now the question is, what CPA tries to do is, the CPA basically knows that, you know, like one of these keys is correct, right. He knows that, say suppose k star is correct, and therefore the column corresponding to k star, right, should correlate somewhere with these columns. Okay. Because there is a real power trace being observed here and this is your hypothetical power. At some point of time there should be a correlation. That means, you know, like this should correlate to either this time instant or this time, you know, for example in the simulated power trace there are 12 time instances. At some point, right, there should be a correlation. Whereas for the wrong key, that means if I consider any other key, right, like k which is not k star, okay, that means for any other wrong key I will never get that correlation. Okay. And therefore I can distinguish the correct key from the wrong key. So this is the broad philosophy of correlation power attacks, and now let us see, you know, like how we can understand it better. Okay. So this similarity is essentially very vital, and you can use any other similarity metric, but one of the most popular ones is what is called as Pearson's correlation metric. So basically again we try to compute correlation coefficients for the simulated power traces for AES. Like before, we simulated the power profile for an iterative AES, this time by using say the Hamming distance, because last time we were using the Hamming weight. So let us try Hamming distance again, you know, you can again try Hamming weight as well. So if we try Hamming distance power model and we apply it on the state registers, update it after every round, and then we store it in again this matrix which is called as trace indexed by n sample and n point. So if you remember, right, the real matrix that I showed, you had, you know, like 10,000 for example on one side, that is your n samples, number of encryptions you are doing, and on the other hand n point basically is in, you know, the number of time instances the point where you are sampling your power probe consumption. Okay. So in this case, in the simulated environment, n point is 12. Okay. So n sample is the number of power traces acquired and n point is the time instances for which the power values are observed. Here n point is 12. Okay. So the next thing that we will see is how do we calculate the hypothetical power. Okay. It is quite straightforward but little tricky because of the AES shift rows. Okay. So let us try to observe this, how it works. So for example, when you are finding out the Hamming, you know, like say you are applying the Hamming distance power model, so then it matters, like you need to observe that this is your corresponding register where you are storing the input of the 10th round and also the output of the 10th round. So therefore, right, any register, if you want to calculate the hypothetical power because of a register, then you have to basically find out what is the content before and after and take the Hamming distance between them. Okay. So for example, let us consider R0. So if you are considering R0, then you are basically finding out the distance between C0 and S0. Okay. And therefore, right here you know that you know, like C0 is given, you know, like that is basically stored here in this table, and C0, right, if you want to C0 and S0, and you see that S0 you can get from this equation, because S of S0 XORed with K0 is equal to C0. So therefore, if you want to predict S0, right, you have to basically XOR C0 with K0 and find out the inverse of it. Okay. So this is quite straightforward. On the other hand, if you are targeting say R1, suppose you are targeting, so this is fine for R0, right. So if you are now targeting R1 for example, so then that means that you are basically targeting this, right. And now you can observe that you have to observe or find out the Hamming distance between S1 and C1. Okay. So, you have to find out the Hamming distance between S1 and C1. Okay. But you can observe that the content of S1 can be got from this byte, can be got from C5. Okay. Because if you want to get S1, then because of shift row, you have the equation which is S of S1 XORed with K5 is equal to C5, and that implies that S1 is equal to S inverse of C5 XORed with K5. Okay. And that is basically written over here, that you have to target C5 and K5. Okay. So, likewise you can work out the remaining things, but it is important that when you are implementing, you have to take care of the shift rows, otherwise you will get wrong results. When you are particularly when you are applying Hamming distance power models, when you are applying Hamming weight power models, it is probably more straightforward, you need not bother about this. But when you are trying with the Hamming distance power model, you need to take care of the shift rows. Okay. But that is easy. So, now so once we have done that, we basically we can go to the next step, which is computing the correlation matrix. So, here you have got the actual power values for all the n sample encryptions which are stored in the matrix trace n sample endpoint, as we have seen. However, you should reflect on the point that we are calculating the hypothetical power using Hamming distance, and therefore, the trick that we saw in previously, right, when we were talking about the Hamming weight power model will now not work. Okay. You cannot just store based upon the only a byte. Okay. And that is why you probably need a bigger data structure. So, let us use again all the n sample points. Okay. And the other point is like that attacker, right, first scans each column of this array and computes the average of each of these columns. So, basically what now the attacker does is that attacker wants to calculate the correlation between each of these columns, like basically wants to calculate the correlation between a column of the real matrix T with your hypothetical power matrix. Okay. So, basically for every column, if you want to calculate the correlation, therefore, you need their individual means. Okay. And their individual means are here denoted as a mean trace endpoint. Okay. Note that why endpoint, because every column, right, will have one mean, and there are endpoint such columns in the real matrix. So, therefore, mean trace will have endpoints. Okay. Likewise, for the hypothetical power matrix, you know that it is indexed in the column by n key, that is the number of possible key bytes, which is say 256, and therefore, the attacker can scan again each column, and therefore, the average for that column is stored in the data structure or array, which is mean h. Okay. And the number of possibilities is n key. So, you have got mean h denoting the average for the columns of the hypothetical matrix, and mean trace storing the average for your real power matrix, which is T. Okay. So, then we are all set to calculate the correlation matrix. So, here is basically what we are doing. You have got the hypothetical power matrix, you have got the real power matrix. Okay. So, let us denote this as your like one of the columns and of your hypothetical power matrix, and you are trying to correlate this with another column of the real power matrix. Okay. And this you are storing in this correlation matrix. So, you are basically taking this and indexing here as the row, and you are taking this column position and indexing that as the column of this correlation matrix, and the value here is essentially nothing but this. So, basically, right, it stores, so Cij will mean that you are taking the ith column of the hypothetical power matrix and you are correlating with the jth column of your real power matrix. And as you know that if you want to correlate this vector with this value, you have to you can just straight away apply Pearson's correlation, which means you have to basically find out the covariance and divide it by the product of the variances. So, you have to calculate the variance of each of them, and then you have to divide by their product. Okay. So, that is exactly done here. The numerator stores the covariance and the denominator stores the product of the variances. Okay. So, like if you are very accurate, maybe you have to do a square root and stuff, but more or less you get the same value. So, you get the same proportionality. So, you need not bother about like applying the square root here. So, therefore, right, therefore, now you basically observe this correlation matrix, and the idea is that you have got n keys. So, remember that the rows are indexed here by n keys, and the idea is that what you expect basically is that for the correct key, that is suppose your correct key is k star, you will find out one non-trivial value here in the correlation, Whereas if your key is wrong, then probably what you will see is that all of these values will be less, much lesser. Okay. So therefore, you basically try to identify the correct key, or the correct key row where you get a non-trivial value of the correlation. Okay. And that basically distinguishes your correct key from the wrong key. Okay. So here is an experimental result which has been developed on simulated power traces. So what we have done is basically again done our like simulation. So you have basically simulated the power traces by Hamming distances here of the registers after every round. So you are basically calculating the Hamming distance with a particular round with the previous round, and then you are basically trying to find out the corresponding, you are applying CPA to develop to distinguish the correct key from the wrong keys. Okay. This is again like a similar analysis, but here we have basically added noise, and therefore although there is a separation, but the separation comes little later compared to the in this case where there is no noise. Okay. So of course, like when, as we will see later on, when you are trying to do this analysis with actual power traces, then you have got more phenomenon which you need to kind of accommodate. But at the same time, the technique remains the same, and if you understand this and if you are able to apply it on simulated power traces, then we have a good amount of understanding about how the attack works. Okay. So therefore, let me summarize this discussion on correlation power analysis. So basically, right here we have got like say d number of plain. So let me so again you can also visualize this attack say from the perspective of the plain text. You can do it either from the plain text or the cipher texts. So you have got say d number of plain texts or cipher texts that you have taken. These are your corresponding key hypotheses. That means again in our context of AES there are 256 possible hypotheses. You calculate the intermediate round. So this is the intermediate round of your cryptographic algorithm. So basically when you are doing it from the plain text, you will not calculate the inverse S box, but you will apply the forward operation. So you basically take the plain text portion, XOR it with your guess and calculate the S box. Okay. And you will find out say you basically will get the state. Okay. And that state essentially is denoted here as the hypothetical intermediate values. Hypothetical why? Now because you are guessing the key, that is why it is hypothetical. You do not know whether that is the actual state or not. But then what you do is that you basically, in order to understand whether it is the correct one or whether it is wrong, you basically apply your power model on the hypothetical state. Okay. So when you are applying your power model, suppose you are applying the Hamming weight or the Hamming distance or any other thing, for example, whichever is your favorite power model. So when you are applying say the Hamming weight, so now you basically take say V11, which is your hypothetical intermediate state, and then you basically apply, so take V11 and say calculate the Hamming weight. So this Hamming weight essentially gives you the hypothetical power value. Okay. So therefore you get H11 and you do it similarly for the entire operations. Okay. But how many such matrices will you get? Okay. You are basically getting it right. I mean you are getting the hypothetical power value, but observe that the hypothetical power value, right, which you are observing is for a specific byte. Okay. But then if you change the input, that means if you change the if you do it for all the d possible values of the plain text, you will get d possible values of the hypothetical power trace, and you will get it for every key guess that you do. Okay. And that essentially is nothing but your matrix H. So this is your hypothetical power matrix H. Okay. And now you basically observe the actual power consumption. As we discussed, the actual power consumption is denoted by the matrix T. Okay. So note that T is indexed again in the row by the number of encryptions you are doing, that is d encryptions which you are doing, and then the column is the time instant. So here is a power trace, for example, you can see it is the voltage versus time plot, and this is the time which you are observing. Okay. And therefore now you have got two matrices. Okay. And now you basically try to correlate the one of the columns of the hypothetical power matrix with your real power matrix, and that gives you the I comma jth position of your correlation matrix. Okay. And that essentially, as we have discussed, is noted over here, and then the correct key is returned by finding out the max of these correlation values. So basically what you do is you try to find out the maximum value in the correlation matrix. Okay. The corresponding row gives you, or the corresponding index of the row gives you the correct candidate key, right? Because what you are expecting is that in your correlation matrix you have got, so the correlation matrix will be indexed by so you have got, so it is indexed here by the number of possible key. For example, in AES there are 256 possible keys, and it is indexed in this direction by time, right? The idea is that out of all these 256 keys, there is one key which is the correct K star, okay? And note that K star, the operation because of K star will not correlate at all time instances, but rather it will correlate at a specific time instance which is say T star, and that is my point of interest, okay? And the idea is that this value, or the assumption is that this value will be the maximum value, okay? So therefore, I basically try to see this matrix, find out the maximum value, and then just return the corresponding index as my correct candidate key, okay? And that essentially is expected to be the correct key, okay? So that is essentially pretty much what we had to discuss here, and so basically, right, I mean, let us, so this is a reference that we have been following for our discussions, and so in order to conclude this, so what we discussed is that the difference of mean based DPA can be programmed by a systematic fashion. We have seen how to write programs for DOM, that is the difference of mean technique. One can learn that the technique on simulated power traces modeled by like Hamming weight or Hamming distance models without even getting access to complicated setups, okay? You can learn and even develop these techniques, okay? You can try to develop better statistical techniques without even going to going to a costly setup, okay? Likewise, right, we have also seen how to develop that. We have seen that it is important to to also learn the leakage models, and that you can do by modeling the leakage, and that essentially brings us to what is called as the stochastic models of leakage, which can help us to improve accuracy, but albeit it requires a profiling stage, okay? And so the difference of mean and the CPA that we discussed are both non-profiling attacks. As opposed to this, we have something which are called as template attacks, which are examples of profiled power attacks, okay? And CPA is an improved method of DPA and can also be systematically programmed. You can write again similar programs, and therefore you can compare the performance of CPA with difference of mean techniques, and you can try to understand how they trade off with each other in terms of efficiency and as well as success rate. So we will see in the next class about how to define metrics and understand how to obtain the success rates of our side channel experiments, okay? So thank you for your attention.